All right, we're going to look at graphing and motion in this. So to start us off, here is probably the most basic graph that we can look at. Okay, we have, this is a position versus time graph. Position on the y-axis here, time on the x-axis, okay? And you're pretty much always going to have time on your x-axis for these motion graphs, okay? But the question is when we look at this graph, what is it telling us about how the object is moving, okay? And if you look at it and think about it, the object's position, which is marked here, does not change, right? It stays the exact same as time moves on. So this person is just standing still. When you see a graph that looks like this, you're looking at a person that isn't moving at all, okay? Let's look at another one. Here's our next graph. Okay, this one's a little bit different. Notice that this one isn't flat, it has a slope, okay? So again, position versus time, and this person, they're moving in the positive x direction at a constant rate. They're just moving forward at some normal speed, okay? Take a look at this graph. What's the big difference here? Okay, this slope is negative, okay, and that's going to mean something for us, right? Displacement is a vector, which means that direction matters. So if I have a positive slope, like I have in the one in the upper right-hand corner, or a negative slope like the one in the lower left corner, that means something different, right? This new graph that we're looking at here, the person is going backwards, okay? They're approaching the origin or the zero position, whatever that means, but they're headed back towards that instead of away from it. And then this last graph is different from all the other ones. And I could ask several questions about this thing. Are they moving forward? Are they moving backwards? Do they ever stand still? Okay. And as you look, right, this one, the big difference here is that it's curved, okay? We know we're moving forwards because we're getting further and further away from the zero position. So right, if I say that, okay, right here's the zero position, I'm getting further and further away from the zero position, okay? And really, the huge difference here is, look at how steep it is in the beginning. And then look at how steep it is here in the middle. And then look at how steep it is out here at the end, okay? That's telling us something about how the object is moving, and we'll look at that a little bit closer here in just a second. So, okay, understanding graphs using data. What if all I'm given is a data chart? So I've got this data here, and if I look, okay, so time is just moving up 1 second at a time, 0, 1, 2, 3, 4, 5, da-da-da-da-da. Okay, you can see it just keeps growing by 1. But is my position doing the same thing? So I start at 2 and I go to 4.5, so that's, I added 2.5. Okay, and then to get from 4.5 to 7, I added 2.5 again. And then 7 to 9.5, I added 2.5 again. Okay, so if you look at that, you can see that there's a pattern in there, right? Every single second, we're adding 2.5 meters of distance, okay? So I think you can kind of see where we're going with this, right? This is going to eventually tell us that, hey, you know what? We're going 2.5 meters per second, right? Each second, our position changes by 2.5 meters, right? So if I take the data and plot a graph of it, I have this beautiful graph here. All the data points line up. It's a nice line, and so that's another thing that this kind of tells you. Okay, what does the slope mean? What does the y-intercept mean? So the slope of this line, by the way, if you count it out, right, if you do your rise over run, right, you're going to get 2.5. Okay, so essentially, anytime you're looking at a position versus time graph, the slope tells you the velocity. Whoa. And then, so what does the y-intercept mean? Okay, well, the y-intercept is right there. all that's telling me is that at time 0, that's where I am, right? Most of the time that's a starting position. Where did you begin? Did you start at 0? Did you not start at 0? And for us, we didn't, right? At time 0, we started at 2 meters for some reason. And then last but not least, can I write an equation for this line? Sure you can, okay? Y equals mx plus b. And then the beautiful thing about physics is you look at this and you say, okay, on the y-axis I have distance here, so you could replace that with d equals your slope, a number you know, 2.5. X is time, so I can put a little t there, and then the y-intercept plus 2. So d equals 2.5 t plus 2. And that's an equation for that thing, that person, whatever, however they're moving. Okay, a little bit of practice. Take a look at these graphs. Think to yourself, in each of these different sections, what's happening, how is the person moving, think about it, and then I'll explain it. Okay, so in the first graph, okay, the motion changes 3 times, okay? And you know that, you can see that because of the slope, right? Here's one slope, second slope, third slope, right? The motion changes 3 times. In the beginning, this person's moving forward, okay? For 3 seconds, they head out to the 30-meter mark, okay, and then they stop. And they sit there, they do nothing for 3 more seconds until they get to 6. And then after that, notice how this gets negative? They go in reverse, and they head back. And then they have this place marked because they pass their starting position. Okay, they pass the place where they started, and they go back way behind it down here to -20. Okay, now if I erase all of my beautiful lines here. Okay, and if I asked you guys, when were they moving the fastest? Okay, and this can kind of be a little bit of a trick question. When were they moving the fastest? Well, how do I tell speed when I'm looking at a graph like this? You look at slope. You say, okay, look, this is a positive slope. This is a negative slope, so does that mean that this is the fastest because that's positive? The answer is no, okay? Look at how steep this is compared to how steep that is, okay? Right here when they're going backwards, they're going much faster backwards than they did when they were moving forwards, and you can see that in the slope of the line. And then down here, a little bit different story. Start at 20, you sit there, you go forward, you sit there, you go backwards. Okay. So that's kind of what these things mean. It's really important that you can look at these graphs and tell and interpret what's going on. Now, in these next couple of slides, we're going to look at, okay, if I give you the position, can you tell me what the velocity graph should look like? Can you tell me what the acceleration graph should look like? Okay, so you can see right here 3 different position graphs. What I want you to do is pause the video and then predict, draw, what do you think the velocity graphs are going to look like? What do you think the acceleration graphs are going to look like? Okay, try and draw those out. Think about what's going on here. Okay, and then I'll show you the solution. All right, here we go. So if I want to get to velocity, I need to think about slope. Okay, the slope means rate of change. Okay, and so the rate of change of my position, how the position is changing, that is my velocity. So if I look at this and I say, okay, right here in the beginning, look at this line. That's a flat line. That has a slope of 0. So what's the velocity? Well, it has to be 0, and it's 0 the whole time because that slope is always 0. That person isn't moving. Okay, I come down here to this next one, and I look at the slope, and I say, well, there are no numbers on here, so I can't tell numerically what's going on, but that is a positive slope, okay? And so that positive slope means I'm going forward, which must mean that I have a positive velocity, okay? So how do I draw it? I know that it starts positive, but then where does it go from there? Okay, look at that line. Does the slope of it ever change? And it doesn't, right? The answer is no, right? So if that's the case, if the slope doesn't change, the velocity can't change. Okay, so I'm going to have a positive constant velocity. And then down here, negative slope doesn't change, so I have a negative constant velocity. Okay? Look, there's all this stuff we talked about. Okay, so here we go. Next step is to say, okay, take a look at the velocities. Can I turn those into accelerations? Obviously you can, right? And again, it's the same trick. I'm going to look at slope. The rate of change of velocity is acceleration. Okay? If you want to know what the velocity is doing, you look at how the position is changing. If you want to know what the acceleration is doing, you look at how the velocity is changing. So look at each one of these velocities. Do they have a slope? And the answer is no, right? They're in different places, but they're all flat. They all have slopes of 0. And so if they have slopes of 0, their accelerations will be 0 every time. Okay? So looking at this, you can say, hey, I know what the acceleration graphs look like for these types of position graphs. Okay? So what if the positions look like this? These ones are a little bit trickier, but the method of figuring this out is exactly the same. So we're going to start by looking at the slopes. And so what I want to do is I want to say, okay, what is the slope like in the beginning, and what is the slope like in the end? So if I look here in the beginning, the very, very beginning of this curve, okay, the slope is flat. Okay? And then if I look at the end, the very end of this, the slope is positive, right? So I go from a slope of 0 to having a positive slope. And so what does that mean? That means that my velocity is going to start out at 0. And it's going to end at some positive value. Okay? And then I can connect the dots, right? I'm getting faster and faster and faster. And you can see that here in your position graph. You can see that in the beginning, I'm not covering very much distance as time goes on, right? Look at that huge amount of time and that little itty bitty change in distance. But then out here, I have a small amount of time, but that gives me a huge change in distance, right? I'm getting faster and faster and faster, and so I need to see that in the velocity graph. A velocity that's getting faster and faster and faster, okay? So let's move on. Let's move down here to this next one. Okay, what's the slope like in the beginning? What's the slope like in the end? Again, in the beginning, if you look, we're flat. And in the end, we're headed downhill. Okay, so that's a 0 slope and then negative slope. So on my velocity graph, I'm going to start at 0. Right? We're not moving in the beginning. We're moving really, really slowly. Okay? And then I'm headed back towards the origin, right? I'm going downhill. That's a negative velocity. So our velocity graph is going to look like this. Really slow in the beginning and getting faster and faster and faster, but in the negative direction, okay? Again, if you look here, it doesn't matter if the slope is negative or positive, right? This positive slope just means that I'm going forwards. This negative slope over here just means that I'm going backwards. But how steep the slope is, that tells me the speed. So let's fill these things in here. Hooray! And, all right. So if I have a changing velocity, what does that mean? It means we're accelerating. Okay? So I can make acceleration graphs. Check this out. The slopes here, positive slope, negative slope. It means, and it's the same thing as those graphs we were looking at the other time. Okay? If I have a positive slope that is constant, I'm going to have a positive acceleration that is constant. Same thing down here. Negative slope, constant. So I'll have a negative acceleration that is constant. And now, right, I can tie these things together. I can say, hey, look, this acceleration gave me a position versus time graph that looks like this. Now let's try, there's one more example here to see, okay? What if they start us here? What if they say, hey, here's your velocity graph, make the other graphs from the velocity graph? Well, the acceleration one's easy. I look at this and I say, okay, what's the slope like? It's negative. Does the slope ever change? Nope. So it's a constant negative acceleration. But then I come over here and I say, okay, how am I going to get back to position? Okay. So what we're going to do is we look at what is the value of the velocity here? What is the value of the velocity here? What is the value of the velocity here? And so the velocity starts out positive. In the middle, the velocity is 0, right? It crosses the axis. It goes to 0. And down here at the end, the velocities are negative. So think about what that means. What direction am I going in the beginning? Well, positive velocity means I'm going forward. So in the beginning, I'm moving forward. So over here, I've got to start out with a positive slope. I have to be going forward. In the middle, my velocity went to 0. Okay, so that's a flat slope, right? There's no slope there. And then in the end, the velocities were negative. Okay, and so you can kind of see how we've constructed what's going to happen over here in the position graph. And then I just need to connect that with a curve. Whoa, missed the top. Okay, so I've got a curve that looks something like that, where in the beginning, we're fast. We slow down, stop, and then we start speeding up, but in the negative direction. Okay. So we'll fill out the rest of this really fast. Connect it with their curve. And there's motion and graphing. Okay, last little bit is instantaneous velocity. We talk about average velocity. We talk about instantaneous velocity. Okay, you guys should know already that average velocity is just total displacement over total time. Where did I start? Where did I finish? How much time did it take? Divide those quantities and you have the average velocity. But the instantaneous velocity, this is how fast am I going right now? Right? At any given moment in time, how fast was I going? And really, you've got to see a graph to pull that information out. Okay? So here's a graph of position versus time. How could you tell what the average velocity was at, let's say, the first second? So if I'm looking at this and I say, okay, right, so here's the first second, here's where it is on the graph, how are you going to tell what the instantaneous velocity is right then? Okay, well, you should remember, hopefully, that if I'm looking at a position graph and I want to know about the velocity, I need the slope. The slope of that line is the instantaneous velocity at any given point in time until the slope changes, right? What's the instantaneous velocity right there? Well, it's 0, right? It's a slope of 0, okay? So if I look at this and I'm doing slopes and I say, okay, so I start here, rise over run, so I rise 4, I run 1, it didn't really match, but well, this is a little bit easier. I rise 10 and I run 2. So 10 over 2 is 5, right? This is 5 meters per second. This one, I drop -5 in 2. So that's what? -2.5 meters per second. Okay, and then the slope goes to 0, and then here's a new slope, and there's another slope. So the instantaneous velocities are the slopes at those given times. And then the last thing you could see is they could give you a graph of the velocity, and this makes it so easy. If the question asks, what's the instantaneous velocity at 4 seconds? Then I just look at the graph. Okay, this is already velocity, so at 4 seconds I was going 2 meters per second. At the 12th second I was going 0 meters per second. At the 20th second I'm back to 0. At the 17th second I'm right here at -2. So if it's a velocity versus time graph, the instantaneous velocities are really, really easy to get. And that's all I have for you on how to read graphs doing motions. Again, if you have any other questions, send me an email. I'll get back to you, and have a great week, you guys.